Dear students, welcome to this particular module, and in this particular module we will study about the stereochemistry of the compounds containing nitrogen, sulphur and phosphorus. You have already studied about the stereochemistry of the compounds where carbon is the chiral center or there is chirality in the molecule because of their structure that we have discussed in detail. Here we will study about the stereochemistry arising due to these heteroatoms, that is nitrogen, phosphorus and sulphur. If you look at the learning outcomes of this module, dear students, after studying this module, you will be able to understand the stereochemistry of compounds containing nitrogen, phosphorus or sulphur either alone or in combination, and you will be able to explain the effect of lone pair on stereochemistry. So, let us begin learning this module. Any compound containing atom like carbon, nitrogen, phosphorus and sulphur forms a tetrahedral structure with 4 groups attached to them. When their 4 groups are different, as we have seen earlier in the case of carbon, then they exhibit stereochemical behavior. Stereochemistry of compounds containing nitrogen, sulphur and phosphorus gives very interesting and useful information about their application in drugs and medicines. And this has been proved in various fields that the compound in different stereochemical form behaves in different manner. For example, the R isomer of thalidomide is an effective drug to treat the morning sickness in pregnant women, whereas its S isomer on the other hand causes deformities in embryos. So, you can see such widely difference between their R and S isomer, and the structures you can see for these two cases are as shown here. In another interesting example, the interaction of propafenone with respect to 5-hydroxylation is stereoselective in nature, and it has been studied and found that R-propafenone is more potent inhibitor than its S enantiomer with respect to cytochrome P4502D6 mediated 5-hydroxylation, and these are the two enantiomers of this propafenone, the R and S, the structures as you can see here. So, with these interesting examples you can understand that how the stereochemistry has very important effect on the behavior of these molecules, especially in respect to the drug and medicine field. So, with this background, let us start understanding the stereochemistry of the compounds having nitrogen, phosphorus or sulphur in them. Let us begin with the stereochemistry of nitrogen containing compounds. Nitrogen is tetracoordinate in ammonium salts and tricoordinate in amines. This all of you know, and they exhibit chirality with this coordination in organic compounds. Substituted quaternary ammonium compounds and N oxides are examples of tetracoordinate chiral center. Let us begin with amines. If you look at the amines, they are tricoordinate, and tricoordinate amines can be treated in same manner as tetracoordinate compounds. You can say with one lone pair as the 4th substituent. A nitrogen atom in chiral amines has a pair of non-bonded electrons that can turn inside out even at room temperature, and hence undergoes fast amine inversion. Amine inversion is actually, you can say, is an example of conformational isomers, which is also called as invertomers. Chiral amines cannot be resolved due to amine inversion. So, you can see as shown here in the figure that although these two look to be mirror image, but they are so freely interconvertible that they cannot be isolated and put up that okay, this is R and this is S. On the other hand, if we talk about most of the quaternary ammonium ions with no bonded electrons and possessing 4 bonds to the nitrogen, now they will not undergo inversion, that is they do not invert. And because of this fixed rigid geometry, now this will be imparting chirality when all these 4 groups are different. So, let us try to understand what is this concept of inversion, and I will take these 2 pens and my hand to make you understand that. Now, imagine that here we have nitrogen which is joined to one R1 group, another R2 group and another R3 group which is my pen. And then consider and imagine that here is the lone pair. So, how inversion happens is, it will go, all these 3 groups will come here and this nitrogen now becomes sp2 hybridized and you get this transition state where the p orbital has the lone pair, and ultimately the lone pair will shift here, it again goes back to sp3 and you have these 3 groups coming up. So, let me show you again. Now, what is happening in context of each of these bonds is that this is coming here, this is coming here, this is coming here and the lone pair comes here. So, there is a inversion happening, and when you have this inverted molecule and put it on its mirror image, you will find that they will be superimposable, and that is by this inversion it is really getting converted into its mirror image, that is R is getting rapidly converted into S. And this rapid interconversion is happening at room temperature. So, it is very difficult to isolate the independent R and S, and hence when you have this nitrogen with 3, although all the 3 groups may be different, but this type of molecules will not show the stereochemistry of the optically active kind. The moment you have the 4th group here fixed, then there is a rigidity in molecule, and this and its mirror image will be non superimposable, and then these type of the quaternary ammonium type of derivatives will be showing stereochemistry in these. So, dear students, now you can relate, let us look at the figure 1 again, and you can see that these 2 mirror image molecules where you have nitrogen attached to R1, R2 and R3, they are interconvertible through the inversion phenomena, and the inversion happens via this transition state which is this 3. But this inversion of amines can be restricted. Suppose you tie all these 3 groups, because you need flexibility in moving. So, if these are part of cyclic ring system, then again you can stop the inversion, and that will lead to increase in the barrier to inversion. For example, you consider this case which is the Trogger's base, which is shown as the structure here. Nitrogen is placed on a bridgehead, and obviously inversion cannot take place without breaking a bond. Therefore, stable enantiomers are formed which can be separated easily. Another example, if we consider, as you can see here, is the 2-methyl 3,3-diphenyl oxagyridine, which is the structure 5th, which exists in its optically active form, which is levo rotation. So, you can see here that this also will be able to exhibit the stereochemistry. For the substituted aziridines, the invertomer which has the R group anti to the ring substituent is more stable. The enantiomers of amine are termed as invertomers. 2,1-naphthyl aziridines, as you can see the structure 6, exist in the anti conformation, and 2,3-diphenyl aziridine, which is the structure 7, in the cis form. Now, substitution of nitrogen by halogen increases the barrier to nitrogen inversion, and thus 1-fluoro-2,2 bis trifluoromethylaziridine, which is the structure 8 as you can see here, does not invert even at 190 degree centigrade and exists in its most stable conformation. Further on, in 6-membered heterocycle ring inversion and pyramidal inversion, they go side by side and are competitive. In 1,3-dimethylpiperidine as shown in the figure 2, ring inversion leads to conformational isomers and the configuration isomers, that is cis and trans, remain as it is. But in the pyramidal inversion, cis isomer is converted into trans isomer and vice versa. So, you can notice and see all these inversions. You can see from this cis to cis is the ring inversion, and from cis to trans you have these pyramidal inversion, and again from trans to trans you have ring inversion. After studying this, let us now understand the stereochemistry in oximes. The oximes are formed by the reaction of carbonyl compounds with hydroxyl amines, that you are already aware, and they are the chemical compounds with general formula R1 R2 joined to carbon, further joined to carbon is doubly bonded to nitrogen, and then further it is attached to OH, and obviously nitrogen will have another lone pair on it. So, as you know, the oximes are formed by the reaction of carbonyl compounds with hydroxylamine, and they are the chemical compounds with the general formula R1 R2 C double bond NOH. The oximes can exist in tautomeric forms as shown here 10 and 11 in solution, and in this particular equilibrium, the equilibrium lies more towards the structure 10, that is C double bond NOH, and not the C double bond NO, because relatively the 10 structure is more stable. Now, based on the substitutions at this carbon, you have R and AR, and depending upon how they differ, if they are same, then there will not be any stereochemistry, but if they are different, then we can have different type of oximes, and there are two types of oximes. You have aldoximes and you have ketoximes. Now, if they are derived from aldehydes and in this general structure R is equivalent to H, then they will be referred as aldoximes, and if they are derived from ketones and possess R as the alkyl or aryl group, then they will be referred as ketoximes. The oximes show geometrical isomerism due to the restricted rotation of carbon double bond N, that is C and double bond. The term syn and NT are used for oximes instead of cis and trans. Now, in case of aldoximes, the syn form is the one in which both the hydrogen and the hydroxyl, that is the OH group, are on the same side of the C double bond N. The NT form is the one in which both the hydrogen and hydroxyl group are on the opposite side. So, it is according to the positioning of H and OH. If H and OH are on the same side, it is cis analogous and called as syn, and if they are on opposite side, then it is NT. And you can see their structure, the syn and NT forms are shown here. But in case of ketoxime, the syn and NT forms are based on the spatial relationship between the first group given in the names and the hydroxyl group. For example, the ketoxime of 2-butanone can be named as either syn methyl ethyl ketoxime or anti ethyl methyl ketoxime, as you can look at the structure. Why syn methyl ethyl? Because before methyl you have put up syn. So, this means methyl and OH are on the same side. But when we name it as anti-ethyl methyl ketoxime, then this means the ethyl and OH are Nt. So, it is relative to the what alkyl group is syn or Nt to the OH, correspondingly the name is given. Let us also try to understand how do we give the Ez notation to these oximes. The Ez notations are better in differentiating the geometrical isomers of oximes, and the Z oximes have hydroxyl group and the group with higher priority on the same side of C double bond N. However, in the E oxime, they are arranged on the opposite side of the C double bond N bond. For example, syn acetaldoxime will be named as E acetaldoxime or 1-En hydroxyethanamine. Since the hydroxyl group and the group with higher priority, that is the methyl group, are on different sides of the C double bond N bond. On the other hand, the anti-acetaldoxime is named as Z-acetaldoxime or 1-Z-N hydroxyethanamine. Since the hydroxy group and the group with the higher priority, that is the methyl group, they are on the same sides of the C double bond N bond. So, you can clearly see that why this particular one is Z, you can see the methyl and OH are on the same side, and why this particular one where the methyl and OH is on the anti side, and you can clearly notice that out of H and methyl, it is the methyl which is having the higher priority, and that has been compared with the positioning of the OH. So, if the higher priority group on the carbon is on the same side of the OH joined to nitrogen, then it will be Z, and if they are on the opposite side, then it will be E. After understanding this, let us understand those cases where nitrogen compounds have double bonds between two nitrogen, that is the azo compounds. The azo compounds are an important class of compounds, and this account for almost 60 to 70% of all dyes. Geometrical isomerism will be possible here in the compounds containing nitrogen double bond, and it plays role in their property. The cis and trans isomerism in these compounds are usually designated as syn and anti respectively. The change from trans or anti, which is preferred isomer form, to cis can be effected by exposure to UV radiation. And if you look at some examples of the nitrogen compounds containing double bond, they include diazosulfonates as shown in this structure here, 15th, diazocyanides, the 16th structure, azobenzene, the 17th structure, azoxybenzene, the 18th structure, orthonitroacetophenone azene, the 19th structure. So, you can see why they all will be exhibiting this geometrical isomerism. The Ez notations have also been used for these compounds, and this is based on the presence of two highest priority atoms or groups on the same side or opposite side, and here it is very simple. You can clearly look at the groups because rest are only lone pairs, and when the atoms or groups are on opposite side, it will be the symbol E which will be used, and if they are on the same side, it will be the symbol Z which will be used. For example, if you look at these two cases of azobenzene, then this particular structure is E-azobenzene. You can see the two phenyl groups are anti to each other, and this one is Z-azobenzene, and these two phenyl groups are on the same side, and that is why this is the Z-azobenzene. And out of these two, obviously you can guess the E will be more stable because of the steric hindrance. Let us now consider fused bicyclic systems containing nitrogen in ring. Quinologidine as shown in this structure 20th and decahydroquinoline as shown in this structure 21, they are two important fused bicyclic systems containing nitrogen atom in the ring. Quinologidine is achiral and exists in cis and trans form. The trans form, which is this 20A structure, converts into the cis form, which is this 20B structure. Or it can convert into its mirror image, which is 22B dash. The 3 conformers are in dynamic equilibrium. The cis form is less stable than the trans form by 18.5 to 20 kilojoules per mole. So, you can see how their interconversion or the equilibrium is established. So, you can see here from this 20A how this 20B dash by conversion is happening, the free rotation, and the 20B is not interconvertible into 20A. So, you have clearly these 3 stereoisomeric forms. Further, decahydroquinoline exists in cis and trans form. As you can see in the structure shown here, pyramidal inversion at nitrogen in the trans form gives rise to invertomers, which are 21A and 21B structures as shown here. Here nitrogen to He, that is He means hydrogen atom present at equatorial position, is preferred. In the cis form, the 2 conformers are obtained by the ring inversion. After studying about the stereochemistry of nitrogen, let us now understand the stereochemistry of phosphorus compounds. Like nitrogen, phosphorus with symbol P is the same group of periodic table. It also forms tri-coordinate and tetra-coordinate compounds having stereochemical behavior. The stereochemistry of phosphorus compounds started in 1950s, and some of the biological transformations are also studied with 4 coordinate phosphorus derivatives. Phosphonium compounds you can see as shown in the structure 1, phosphine oxides as shown in the structure 2, and phosphines, that is the structure 3, have phosphorus as chiral center when all these substituents are different. Here you are shown examples having methyl, phenyl, and propyl, benzyl and so on, but it can be anything. So, when all these substituents are different, then all these cases will be having chiral centers. Phosphines, just like amines, exist in trigonal pyramidal structure form, and tertiary phosphines cannot be resolved easily, again due to the same phenomena, which is inversion, very similar to the tertiary amines. However, inversion in phosphines is slower than in amines, and it can be brought to 0 by increasing the weight of the substituted groups. For example, on replacing 3 hydrogen atoms by deuterium atoms changes the frequency of inversion to 6 into 10 raised power 3 as compared to 5 into 10 raised power 6. The optically active phosphonium salt and phosphines act as precursor for the synthesis of optically active phosphorus. Phosphines on treatment with hydrogen peroxide, they get converted into phosphine oxide with retention of configuration. For example, S plus methyl phenyl propyl phosphine reacts with hydrogen peroxide to get or to give S plus methyl phenyl propyl phosphine oxide, as you can look in this particular scheme shown here, and this process is useful in the preparation of phosphine oxide with absolute configuration. So, this process is useful in the preparation of phosphine oxide with absolute configuration as shown in this particular case. The tetra-coordinate pentavalent phosphorus esters, they undergo nucleophilic displacement reactions at phosphorus in highly stereoselective way, leading to complete inversion or retention of configuration. And these possibilities are dependent on the functions of the nucleophile, leaving group and the reaction conditions. So, what are these dependent on? Functions of the nucleophile, leaving group and the reaction conditions that you have to keep in mind. Phosphorus sulfides are another group of compounds studied widely for stereochemistry, and with this we now move to understand the stereochemistry of sulfur compounds. Chiral sulfur compounds play important role as catalyst and or reagents in asymmetric synthesis. The sulfur compounds possess higher pyramidal inversion barriers than amines. Also, this has been observed that the chiral phosphines and sulfonium salts are stable at room temperature with respect to their configuration, whereas the acyclic amines racemize very easily. Hexavalent sulfur compounds as shown in structure 1, sulfonium salts as shown in structure 2, sulfoxides as shown in structure 3, they consist of sulfur as chiral center, and depending upon the groups attached, if they are all different atoms or groups, then obviously the stereochemistry will be arising. However, the sulfones 4, which also possess sulfur bonds tetrahedrally, do not display chirality due to the presence of 2 oxygen atoms on sulfur. But if sulfones contain different isotopes of oxygen, like if one is O16 and the other is O18 as shown in this structure 4, then they will show chirality. So, there is a stability of pyramidal configuration. We can say chirality increases with increase in atomic number. Therefore, inversion in sulfur compounds is again quite low, unlike nitrogen compounds. Further, you can look at this structure 4. It is illustrating the chirality due to 2 alkyl groups differing only in the isotopes of carbon, that is 12 carbon versus 13 carbon. So, you can see how the chirality can be achieved by making this minor difference in terms of different isotopes of carbon. Furthermore, let us look at this example. Cyclic 1,4-dithiene as shown here in the structure 5th exists in 2 geometrical isomeric forms and ring exists in the chair form. In trans form, the S double bond O, you can see it is, they are trans and they are at axial position. So, that is how this molecule will be existing in the cis form and the trans form, and since they are both equatorial and in trans these are both axial. Let us now try to understand one important effect, which is anomeric effect in dithiene. Sulfur containing compounds show anomeric effect where polar groups bonded to C1, that is the anomeric carbon of glycopyrenosyl derivative, have a thermodynamic preference to occupy an axial position rather than equatorial position. For example, look at this particular structure 6, that is trans 2,3-dichloro-1,4-dithiene. It exists in diaxial conformation due to greater relaxation of the 1,3 diaxial interactions. Tetravalent phosphorus groups, they prefer axial positions in 1,3 dithiene, as you can look at the structure 7, and in 1,3,5 trithiones, which is the structure 8. Cyclic sulfosides on alkylation result in trans stereochemistry between the sulfoxide oxygen atom and new alkyl group as the oxidation proceeds faster from the exo phase. Alkylation trans to the exo oxygen, it gives the desired endo product, which you can see is the structure 9. So, you can see how this endo product is being obtained by the alkylation trans to the exo oxygen. So, I am very sure now you are familiar about how to deal with the stereochemistry of the compounds containing nitrogen, phosphorus and sulfur, and you can look whether these are the chiral centers or not, whether they will be geometrical isomerism coming in them or they will be optical isomerism. So, let us now summarize what we have learnt in this module. Any compound containing atom like carbon, nitrogen, phosphorus and sulphur, if it forms a tetrahedral structure with 4 groups attached to them, and if these all 4 groups are different, they will exhibit stereochemical behavior that we knew. And we further studied that how this can be extended to the stereochemistry of compounds containing nitrogen, sulphur and phosphorus, but in these cases we get interesting and useful information about their application in drugs and medicines. When we talk about nitrogen containing compounds, tri-coordinate amines can be treated in the same manner as the tetra-coordinate compounds, but having a lone pair as a substituent, and because of this lone pair as the fourth substituent, the chiral amines cannot be resolved because of the process which is amine inversion, and I explained how the flipping between the R and S is happening, and so that they cannot be resolved or separated or isolated into individual R and S isomers. Most of the quaternary ammonium ions with no bonded electrons and possessing 4 bonds attached to 4 different groups, they will not invert and they will show the stereochemistry of the optical kind, that is they will be optically active. You can have R and S arising out of these cases. Then we discussed about oximes. Oximes are the chemical compounds with the general formula where R1 and R2 are joined to carbon with a double bond N and further joined to OH, and the nitrogen is also attached to a lone pair, and it can exist in geometrical isomeric forms, that is you can say cis trans or better syn and nt, and they can also be denoted by E and Z that we have understood how, and it is basically the reference of OH taken with a more higher preference group. So, if OH and the higher preference groups are on the same side, it is Z, and if they are on the opposite side, it is E. Then we also studied about the azo compounds, and they will also show geometrical isomerism. The cis and trans isomerism in azo compounds, they are also designated as syn and nt. Then we studied about phosphorus compounds. They also are tri-coordinate as well as tetra-coordinate and showing the stereochemical behavior. Hexavalent sulfur compounds, sulfonium salts, sulfoxides, we considered all of them. They consist of sulfur as the chiral center, and depending upon the groups attached, they will be showing the stereochemical behavior. So, dear students, I am very sure that your understanding of stereochemistry has improved, and the more you practice questions around these, the more you learn and watch these videos again and again, I am very sure that you will be feeling more comfortable in knowing the difficult topic like stereochemistry. You will find it much more easier. Thank you.